Okay, off we go. So, picking up where we left off last time. So, we are almost done with chapter 6. We've got a couple of theorems, couple of cool theorems, fundamental theorem of line integrals, and Green's theorem that we've talked about. Oh, and tenets quiz, tenets code, etc. Clocks ticking. This is a good opportunity for me to do a quick call back to chapter 3. And y'all may recall back in chapter 3, we talked about this sequence of operations, right? If you have a function, you can take its gradient to get a vector field. And then if you have a vector field, possibly a gradient that you just computed. But if you have a vector field, you can compute its curl, and that gives you then another real value function. And I claim that it makes good sense to order those operations like this, to fit the Legos together in this way, not the other way, or not some other way. And I gave you a little bit of an insight as to one cool thing that was about that, because so we made the observation that it's an exact sequence. I didn't prove that it was an exact sequence, but I asserted. And the way I said that is, everything has a lifetime of 2. And we talked through what that means. Okay, so by the way, so the term for that is it's an exact sequence. Okay. All right, so I'm going to try to give you a little bit more of a persuasion of why this really makes sense and how we can actually kind of gain from this, how this is going to help y'all specifically. And I'm going to start by talking about this sequence, which I really do think is pretty naturally, clearly a good way to order things. Because if you have a two-dimensional region and you talk about its boundary, that boundary is going to be a curve. Right, or maybe a pair of curves, something like that. And if you have a curve and you take the boundary, then you would expect that boundary to be a pair of points. Right? And so the boundary operator, defined on, I'm going to call nice regions and nice curves, and let's not worry about anomalous, strange oddities. That's how boundary works. Okay. All right. So if you're willing to believe that this is natural, then let me make the observation that if you look at the fundamental theorem of line integrals here, right? Now we've already talked about, where that comes from, and that's sort of an accumulation of change and that kind of thing. Notice it is a theorem that relates a curve and its boundary points, and specifically by way of a function and its gradient. Right? So this fits very, very naturally on top of that part of this sort of lower exact sequence. Okay, so there's that. And then notice as well, Green's theorem, same story. Green's theorem is about two-dimensional regions and their boundary curves. And, in particular, in terms of a vector field and its curl function. Right? So this stuff up here fits in with this down here in exactly the same way for both of these two big theorems. Right? So now this is what I would call an eyebrow raiser. This is okay, well, I don't know exactly what that means or, why did this happen, but, that is interesting that the pieces fit together so nicely, right? So not only, and we have for some reason this thing just decides to switch inputs sometimes. Come on. Okay. I think we're back. Gosh, I kind of lost my train of thought. So I'm going to pick up at a random point that we were just talking about, and I'll get it back. So we have these two big theorems. We're persuaded that these two big theorems are good. We have this natural sort of boundary operations thing, and this sequence fit together exactly as it is, dovetails very nicely with this stuff down here, right? And it also has this nice feature of the lifetime theorems. which is, again, pretty weird. Now, if we only had one of the two of those things, then you might think, okay, well, that's a weird coincidence, or you rigged it up so that that would work. Now that we have two eyebrow raisers, we should be reasonably suspicious that there might be something really natural going on here. And for whatever it's worth, I'll tell you where this comes from. And the idea of putting these in this order and how that fits so nicely with putting these in this order, it comes from some of the stuff that I kind of vaguely referred to over the past couple of weeks. And a lot of these big vector calculus ideas we're talking about, there is a sophisticated version of this stuff, right? Very powerful, sophisticated math, well beyond what we can reasonably do in this class. That recent math, right? This is stuff that was done within the last 100 years, less than 100 years ago, and what I am showing you here comes straight out of all of that sophisticated stuff. I've taken some what we call chain complexes and co-chain complexes and kind of boiled off all the formality and abstraction and just, in terms of, okay, yeah, but how does that affect us in R2 specifically? And where does the rubber meet the road? What does this actually look like? And this is it. Right? So what y'all are getting here is a glimpse, kind of shadows, and vague glimpses of some very powerful stuff. That, again, is where all this comes from. So I'm going to show you another cool thing, a couple of cool things about this diagram. And by the way, there's this file called diagram.pdf that I'm going to start working on because it's a little bit more roomy and a little bit more sort of, a little bit more full, a little bit more to work with. Y'all can get your own copy of this. It's on the website if you click on class materials from the class website. And here it is, diagram.pdf. It's right there. Right, so get yourself a copy of that. And we've made this observation that these fit together like so. Notice I'm using this term GRN. That's how long ago it was that I produced this diagram. I was still using GRN. All right, so we're back to curl now. Keep in mind, this just means curl. Okay, and you can see the boundaries like so. And you can see our two big theorems, fundamental theorem of line integrals and Green's theorem. And recall, we've spent a fair amount of time talking recently about some very special vector fields. Unusual vector fields. Not all vector fields are in this collection, but there's a small number of vector fields that are gradients of some function. Right? And we've made a series of observations about those vector fields. Another one of the observations we've made is that curl is 0. And another one of the observations we've made about these vector fields is a little bit harder to put on the diagram, but the following I think is reasonably suggestive. Path independence. The feature of path independence means that if you have two curves that have the same boundary points, in other words, they start and end at the same points, then they will give you the same value for the line integral. So that's just how I'm going to represent this on the diagram. Whatever. This, I'm not making a rigorous argument here, right? So I don't need to be too precise. Okay, so this is a kind of a diagrammatic representation of those properties. And remember, this is three different properties of the same vector fields. We're ignoring singularities and regularity issues and stuff like that. That's not really what this course is about. Okay. So here's another cool thing about the diagram. This, what I'm going to call pattern there, that applies in 2 dimensions. And keep in mind what we have here is this is a diagram, wrong color. This is a diagram of vector calculus in R2. if we look into R3, we're going to have a diagram of vector calculus in R3. This is all coming up in Chapter 7, which we're going to get to really soon. Some of today, in fact, we're going to start in with Chapter 7. And here's the cool thing. One of the cool things is that if you take this this pattern, what I'm going to call a pattern on the diagram describing special vector fields and their various properties, it works in 3 dimensions also. Well, that's actually pretty cool. Totally different context, and all the same results hold. Well, they're not exactly the same results. They're analogous results. They're all going to turn out to be true as well, but here's where it gets super weird. Whoops. And let's see here. Let me zoom in so we can see a little bit better. This is totally a preview. Not only does it work in this position on the diagram, but we're going to notice that it also works in this position on the diagram. The exact same pattern. And that is shocking. Super, super shocking. We're no longer talking about vector fields that are gradients. We're talking about vector fields that are curls. I'm no longer claiming that curl is 0. I'm claiming divergence is 0. I'm no longer claiming this thing called path independence, where if you give me 2 curves with the same boundary points, you get the same line integral. Now I'm talking about something we don't even really have the tools to understand yet, but I'm claiming, this all is going to get fleshed out. These special vector fields have the feature that on any 2 surfaces, as long as they have the same boundary curves, will give you the same value of this, whatever that thing is we haven't even talked about yet. It's going to be called a vector surface integral. Haven't even defined it yet. So I hope this is, like I say, an eyebrow raiser. I hope this persuades you that there's some deeper stuff going on. And I hope you're starting to maybe be persuaded that this diagram is a pretty useful way to understand things. If only from the fact that what we have here is what you might call a pattern. You can learn this one pattern, and it will apply to this collection of vector fields that have these properties. It'll apply to this collection of vector fields that have these simultaneous properties. And it will apply to this collection of vector fields that have these properties. You don't have to learn 3 entirely different collections of properties in 3 different contexts. You learn one pattern. And that pattern applies everywhere on the diagram that it fits. Everybody see what I'm talking about? This is a really useful tool. This will help you organize ideas in your mind as we go through. We are going to go through and talk about all the ideas. We're going to go through and talk about, the 3-dimensional operators, and we'll make sense out of what this thing here is, this idea of a surface integral, whatever that means, right? Et cetera, et cetera. As we go through and do those things, keep these patterns in mind. The patterns keep working. Okay. All right. Okay, let's see here. Back to where we were here. Okay, we've talked through all that stuff I wanted to do. On to finding antigradients. I'm going to go full screen now. So this is fulfilling a promise that I made you all a while ago. Remember, we did an example, our very first example using the fundamental theorem of line integrals. I pulled a rabbit out of a hat and I said, here's the antigradient. I didn't give you any sign of where I got that from, right? So here it is. And very reasonably, you probably were thinking to yourselves at the time, how am I supposed to, I don't know how to pull a rabbit out of a hat. How am I supposed to find antigradients? Right? So here's the method. If you have a vector field and you would like to understand it as being a gradient, specifically, understanding it as a gradient means finding that function the anti-gradient. Okay, well, if the vector field is a gradient, then its components are partial derivatives. All partial derivatives of the same anti-gradient. Which gives us these three equations. Now, these three equations, these are all statements about partial derivatives. And, of course, you can take any statement about derivatives and turn that into a statement about antiderivatives, right? Just kind of passive tense to active tense or what. I mean, it's kind of the same statement, but, just kind of said in a slightly different way. So these are basically those same statements. But don't forget, when you write down a statement about an antiderivative, don't forget to add in your plus c. Now let's talk about that plus c for a second. Why do we add a plus c? I'm sure you all remember from way back when. The whole point is that plus c, when you add in the plus c, kind of nothing happens, right? This c, this is a constant that if you have that constant in here where this f is, well, yeah, but then when you take the derivative, it just disappears, so nothing happened, and you basically get to add that in for free, and it doesn't cost you anything. Or said differently, since you could add it in for free, you kind of have to add it in because otherwise, you're just picking an arbitrary antiderivative, and we want the general antiderivative. Okay. So the observation to make here is that if we ask the question, what is it that I can actually add into an antigradient and have the x partial be 0? In other words, what can I actually add for free here? Well, it's not just constants. It's any function of only y and z. Any function that doesn't have x's in it, same deal. You take the x partial, both sides here, you're still going to just get p because the x partial of something that has no x's in it is still 0. Everybody happy with that? There's a little bit of a weird idea. In single variable calculus, an integration constant is literally a constant. With partial derivatives, an integration constant is what we call a partial constant function for this reason. Okay, so likewise for the when you do the y antipartial here and when you do the z antipartial here, so we get these partial constant functions. Now keep in mind, the whole point to all of this is that this f has to equal all three of these things in order for all three of these equations to work, and therefore for our function to be a gradient. Our vector field to be a gradient. So what I need is for these three things to all be equal to each other. And that's the game. This is how we're going to do it. I'm going to show you an explicit version in just a moment, but the game will be write down these antipartials. Don't forget to add in your partial constant functions and then try to figure out what those partial constant functions could be to kind of make everything fit. Let's do one. So here is a vector field, and I would like to know what the antigradient is. Namely, I would like to find what is the thing whose gradient is that function. We're going to do exactly as we said on the previous page. I'm going to take this and do an x antipartial of it. I'm going to take that, do a y antipartial of it. I'm going to take this and do a z antipartial of it. Now the calculus on that, when you're taking antipartials, it's just like antiderivatives. The only tweak is don't forget, one of the variables is a variable. The other two variables, you treat them as constants. Because we're talking about partial derivatives, not single variable derivatives. So with that in mind, here's what we get. These, ignoring the integration constants, these are the anti-partials. And then, by the way, of course, we do have to remember those integration constants. Air quotes, constants. Partial constants. Okay. And the game has begun. I need to be able to make all three of these things equal to each other. I need to find a function that's equal to all three of those things by making appropriate and clever choices of these partial constant functions. Now, I'll show you how I do this. I think the following is a reasonable strategy. I notice two of these expressions have an x squared y in them, and I would like to feel like, okay, well, look, if there's an x squared y in these two, and if all three of these things have to be equal to each other, I kind of feel like we're supposed to have an x squared y here. I don't see an x squared y here, but I get to pick these partial constants however I like. I could just make that x squared y, and now all three of these three purple expressions that I need all to be equal to each other, well, they are, so far at least, in terms of that x squared y term. Everybody with me? And then, etc. So, those are all xz. These are all minus yz squared. And we win. We now have a function that's equal to all three of those things. That's an anti-gradient. Everybody on board? Now, I think it's a good exercise. I want to encourage everybody to do the following. Take this function and take the x partial, confirm you get that. Take the y partial, confirm you get that. And take the z partial, and confirm you get that. Just to double check, just make sure that this actually worked, and that this game that we just won was actually gave us the real win that we needed. So good double check, and give that a quick glance. Okay, now we won the game, good for us, but frankly the game was rigged in our favor because this vector field that we started with, you can easily compute the curl, confirm that it's 0. Remember the theorem we talked about last time, if the curl is 0, then it's definitely a gradient of something. We know, therefore, that there is an anti-gradient out there somewhere, and so the fact that we found it, well, okay, good. I mean, yeah, we found the thing that we already knew existed. Okay. Sometimes there is no anti-gradient, right? Sometimes the curl's not 0. And if there is no anti-gradient, we better not find one, right? Wouldn't that be creepy if we knew for a fact there's definitely not an anti-gradient, but somehow we found something that would have us believe that it's an anti-gradient? That would be bad, right? So let's see how that does not happen. And so here we go. Here's a vector field, and you can take the curl, and you can confirm that curl is not 0. So there is no anti-gradient. Oh gosh, typo. Man, nobody's ever pointed this out to me before. This is supposed to be the anti-gradient. That's the little f. Sorry about that. The anti-gradient little f doesn't exist. Gotta remember to change that. Okay, so there is no anti-gradient. Let's try to find one. Let's see how we will fail to find the thing that doesn't exist. And we play the usual game. We take, let's get back into highlighter mode. We play take the x anti-partial of the first coordinate. We take the y anti-partial of the second component. And of course we get this. And don't forget your integration constants. And here's the game. What can I pick to be those partial constants so that both of these lines will be equal to each other? And I think you can see the cards are stacked against us here. There's no way to win this game. we lose. Thankfully. Right? Again, you don't want to find something when you know it doesn't exist. Does that make sense there? Is everybody happy with the... All right. Okay. Okay. So, moving along into chapter 7. Let me remind you, we are going to eventually have to make sense out of that thing, whatever that is. Again, this is called a vector surface integral. The way we're going to make sense out of it is, first we're going to define something called a scalar surface integral. By the way, you may start to be noticing it's tracking how we did line integrals. First we defined a scalar line integral, and then eventually a vector line integral. We're going to do the same thing here. Well, the way we made sense out of scalar line integrals was to parameterize curves and do a pullback through the parameterization. We're going to do the same thing here now. Whoops. I thought I had... There we go. We're going to talk about parameterized surfaces and take it from there. Okay, so good news. We've already done one. A parametric surface gives position in space as a function of two parameters instead of just one. And here's the example we saw long ago. This is back in section 1.5, and there was a related homework exercise. I'm sure y'all all recall. I claim this is we didn't use the term at the time, but this is a parametric surface because we're going to find position on the plane, anywhere you need to get on the plane, and I can view that position in rectangular coordinates in terms of two parameters, S and T, that basically tell you, y'all remember the geometry down here. S tells you how far to go in the V1 direction. The V1 direction is given. And T tells you, in some sense, how far to go in the V2 direction. And the V2 vector is also given. That look familiar to everybody? Feel free to decide for yourselves if you might want to go back to section 1.5 and remind yourself of that, the details of that discussion. Okay, so position is a function of two parameters. This is straight up, immediately, a parametric surface. Okay. So what I'm going to do for most of the rest of today, pretty much, is just show you more examples of how to create surface parameterizations. And y'all will recall when we did parametric curves, we spent a bunch of time talking about how to parameterize curves. Just different techniques, different useful methods. And so, same story here. Okay. So, my favorite method for parameterizing a curve was the graph parameterization, you may recall. Well, my favorite way to parameterize surfaces, also graph parameterization. It's the same basic trick. Keep in mind, if we're talking about a graph, that means I've got one variable written as a function of the others. So presumably we have something like this. This applies only to graphs. In other words, we have to have it written like so. And the big trick for parametric curves was to let your parameter be the input variable. Here, we're going to let our parameters, plural, be our input variables, plural. Same idea. And it works. It just works like totally awesome. So here's a nice example. We have this equation given to us. Notice it is a graph. Z is a function of x and y. So I'm going to do as promised. I'm going to let my input variables be my parameters. And then it's all over but the shouting. Because if x and y I already know are s and t, then I kind of have to have z be s squared plus t squared. And it's over. We've won. We have position as a function of two parameters. How we doing? Everybody all right with that one? World's easiest surface parameterization technique. All right. Now, again, there's nothing magic about x and y. This works for whichever two variables are the input variables. I'm about to show you an example where x and z are going to be the inputs. Let's see those details. In this example, notice that the equation does not come written as a graph. Sometimes you have to do a little bit of legwork. Sometimes you actually have to solve for one of the variables actively. By the way, your first instinct might be to try to solve for z, because usually, very often anyway, z is a function of x and y, but you can't. Right? So we try to solve for z, and you're not going to be able to, but we can solve for y. And if you solve for y, you get this. My input variables are now x and z. I'm going to let my parameters be x and z. And plug that in. And it pretty much forces me to have y be all of that. So same basic idea, just don't get attached to particular letters of the alphabet. How we doing? Is everybody happy with that? Any questions? Everybody's good. Okay. Cool. The coordinate systems work just fine too. And this is totally analogous to a two-dimensional parametric curve example that we saw with polar coordinates. And the big idea is just kind of insert your coordinate conversion formulas. We're going to do spherical coordinates here. Just insert those conversion formulas, and then again, if you have one variable solved for as a function of the others, then everything just kind of falls into place. And here you go. In this case, we've got rho as a function of phi and theta. Now, a lot of students get weirded out when I say rho here is a function of phi and theta. Right? They don't see the theta. So how is this a function of theta? Well, it's a really easy function of theta. The theta dependence is super convenient, right? It still counts. No problem. This is just a boring function of theta. Okay, so that said, rho equals cosine phi. Fine, stick it in there. Again, all there is to it, right? And having done so, notice the punchline is I have rectangular position as a function of two parameters. Now, in this case, you'll notice there are no s and t. Why did I do this thing where I plug in, I'm not going to leave x and y. I'm going to replace them with s and t. And I do that because I don't want to have a confusion of variables problem. That always just gives me the willies. I feel like you shouldn't have, for example, an x and a y that are both input variables and output variables, right? That's just nails on a chalkboard, right? That should give you the willies too, right? And we've seen how that really does lead to problems when you're doing things like the chain rule, right? So just don't confuse your variables. And here we had to deal with that by replacing them. Here, we didn't. The fact that we were converting between spherical and rectangular kind of did that for us. Right? So I'm just going to leave these as phi and theta. If you want to rewrite them as s and t for whatever reason, I suppose you could. But then you lose the convenience of the theta and the phi representing something geometrically that you already have familiarity with. So I encourage leaving it like this. How are we doing? All right. Okay, this next example, we're gonna skip. You're not responsible for it. You don't have to. The reason I put this in here in the notes is, when time permits, I like to go through it. It's a nice exercise. It's kind of a surface analog of the bicycle wheel example. Do y'all remember the bicycle wheel example? There was a lot of details involved in that, but the big punchline of the bicycle wheel example was rewrite something complicated as a vector sum of things that are simpler. The simpler elements that go into it, much easier to write down, and then just use vector algebra to add them. Right? So same deal here. This is just parameterizing a surface instead of a curve, and I had to come up with a weird example to make it practical. How often does this technique come up in the real world anyway? Very little in my experience. I'm sure there are some contexts where it comes up more. I wouldn't know what those are. So anyway, for our purposes, this is not going to be. I'm not expecting this to be part of the course. So feel free to ignore this example. But if you want to look for something to cut your teeth on, this is a cool example to look at. Okay, this example, very important, comes up a lot. I use this technique I'm about to show you many, many times. Again, mostly as part of my second major in physics. So. Okay, so let's parameterize this shape called a torus. And the torus, you may know already, but the torus is the surface of a donut. The glaze part of the donut. So how do we, okay, I need x comma y as functions of a couple of parameters, and how do I go about doing this? So here's the idea. Create a coordinate system. Now let's talk about what I mean by that. I'm going to start by talking about planet Earth, right, or the globe that we live on, and if I wanted to describe my location here right now to someone who's on the other side of the world, would I give X, Y, and Z coordinates relative to the, North Pole and the stars? My God, no, of course not. That would be crazy, right? Why would I give X, Y, and Z? That doesn't make any sense at all. That X, Y, Z coordinate system, if you know you're on the surface of the Earth, that coordinate system is not tailored to the geometry of the surface that I know I'm on. Right? Does that make sense? So I give latitude and longitude. Of course we would give latitude and longitude. Right? We know we're on a two-dimensional surface, and let's see if I can get this right. So longitude says how far east-west, kind of like theta, sort of. Right? And then latitude says how far sort of north-south, right, which is kind of like phi, just except measured off of the equator instead of measured off the North Pole. So longitude and latitude make loads of sense. That those coordinates are tailored to the geometry of the sphere surface. So when I say create a coordinate system, what I mean is let's dream up, tailored to this surface, how would I describe locations on this surface? And here's what I think makes the most sense. It's going to be sort of vaguely kind of a longitude and latitude kind of like things. I would say, well, first I'm going to pick a starting point. That's going to be our base point. And you know what I'm going to do? I'm going to zoom in so we can see a little better. And if I wanted to describe, you know what? Let me pick a different color. There's our starting point. And if I wanted to describe some arbitrary point on the donut, how about this? I'll tell you that angle, T, that says, by what angle do I go around the dough of the donut? And then secondly, this angle, I'll do a better job than that, this angle there, S, that says how far around the hole. Now, forget about math for a second. Just thinking sort of geometrically. If we lived on imagine some funky planet that looks like this, or a space station. Somebody makes a space station that looks like this, and there are kind of reasonably good reasons one might want to do something like that. If you had a space station and you wanted to describe where on the space station you are, I think S and T, as drawn here, would make loads of sense. It's tailored to the geometry of what we're interested in. How we doing? Everybody buy that? So, I claim we're most of the way toward a parameterization then. Keep in mind all a parameterization is position x, y, z. Let me do like this. So R equals x, y, z. Position as a function of two parameters. That's what we're looking at. I mean, this point that I can call x, y, z is described by these two coordinates. Those coordinates are going to be my parameters. And all that's left to do is kind of do the geometry, and I've just got to figure out how to use geometry to deduce from S and T where this point actually is. And so there's a couple of details there. We'll talk through those, some of those details. The rest of the details I'm going to sort of leave as an exercise. But here's the first part of it. I'm first going to solve for this point. That point there that I'm going to call P. And I'm going to argue that it is the sum of that vector there in orange plus, oh golly, color choices. Oh man, do I have to use yellow? Okay, and this vector here actually shows up reasonably well. That vector there, which is this. Now, there's a little bit of analytic geometry there, a little bit of trig, right? Think it through, make sure you can do this. This orange vector, I think, is pretty clear. This yellow vector, you can see it depends on that angle T, and you got to write down the trig and think through those details. I claim you get that. And so we have the coordinates for that red point, like so. And the next thing I would have to do is figure out how to execute this rotation. How do I rotate by the angle S? Rotating by the angle S around the z-axis. And that's another, flashback, rotating by some angle around an axis. Linear transformations, matrices, the columns are the images of the standard basis vectors, right? Remember, we have a structure. We have a sort of a pattern for how to find matrices representing linear transformations. Make sure you can do that. If you are, I know I say this a lot, but I totally mean it. If you're not sure how to do this, if you have trouble with this, come talk to me. I'll be really happy to help you think through these details. One way or the other, with or without my help, make sure you're good with this. Does that make sense to everybody? Everybody good? And we're done. Basically, a little bit of algebra remains. If I can get this thing to cooperate. Here we go. We found this red point, P, here. Oh, come on. Found that red point P. Was that? We have this rotation R, like that. And the point we're interested in, right, X, Y, Z, our purple point that we're ultimately trying to find, is just what you get when you multiply that out. And again, the little details, make sure you can do that. So, how we doing? Now again, don't get lost in the details, right? Yes, there's a lot of details. That's not really the point here. The point is the big picture strategy. Once you have a natural, tailored to the geometric circumstance, once you have a natural coordinate system set up, then it's really just a matter of doing geometry relevant to the circumstance to figure out position as a function of those two coordinates. So I've used this, like I say, many, many times here and there. You might want to think through, like, what if it wasn't a torus? What if it was a cylinder? What would be a natural coordinate system on a cylinder? That's something to think about. Right? What I would use if I had a cylinder, I would use angle to kind of get my hands on the going around part, and then maybe Z. Tell me how far up. Right? Seem like a reasonable choice? And again, you'd have some geometry to figure out how to make sense out of that. Any given geometric circumstance, pick coordinates natural to the circumstance, and then do whatever the geometry requires. Good. Okay, let's see how we're doing. Okay. We'll do just fine here. So you may recall, back with parametric curves, we talked about how to deform an existing parameterization. So same basic ideas again. Here's the unit sphere, otherwise known as rho equals 1. This is a spherical graph. Rho is a function of phi and theta. Really, really convenient function of phi and theta. Plug that into the conversion formulas. Here's your graph parameterization of the sphere. Now that's what I'm going to call the existing parameterization. This parameterization, which you can write out in coordinates like that, that was a one-step parameterization of the unit sphere. And the question is, okay, instead of that, what if I want to parameterize that? Right now, the sphere was easy because I can immediately write down the spherical equation. It's nothing. It's the world's easiest spherical equation. Right? And that's why this was easy to do. I can't do that here. Right? We're in trouble here. I don't know how to write down the spherical equation for this ellipsoid. Right? So we can't use the analogous technique. What I can do is I can talk about how to take my existing parameterization here and deform it. Right? So the deformation, you'll notice, for example, in the equations, it's pretty easy to see. For example, just replacing x with x over a, y'all probably remember, that means that this is just a stretch. Right, this is flashbacks to chapter 2. I've made this observation before. The course is very vertical, right? Stuff that we do earlier is going to be necessary for the thing that we do later. So we have a stretching happening. How do I say we're doing a stretching? Well, stretching means that I need my x coordinates for this blue surface have to be a times as big as the corresponding points on the green surface. I need to make all of my x coordinates a times bigger. How would I make my x coordinates a times bigger? Well, there's what the x coordinate was. And I'm going to make it a times bigger by multiplying those values by a. That literally makes them a times bigger. Does that make sense? Alternatively, you can think of this equation. We can do this stretch by replacing the variable in the equation, kind of like we did back in chapter 2, and that turns that into this equation. So now I claim that these two equations that I have in blue, same equation, pretty much. This first equation says x equals a sine phi cosine theta. This second equation, well, I mean, if you take this a it's in the denominator of the left and you move it over to the right, it's again x equals a sine phi cosine theta. Exactly the same. So take your pick on how to think about it. If you want to think of this as literally multiplying by a the existing formula for x, or if you want to think of it in terms of replacing the variable x with x over a, morally equivalent, whichever one is intuitively more satisfying to you, go ahead. I encourage you to try to get comfortable with both of them. Likewise for Y and Z, by the way. Okay. How we doing? Let me pause real quick. Everybody all right with that? Okay. And a real quick last thing, and then we'll call it a day. This next page, you'll see it says for students to read, won't be covered in class. Next time I'll hit some very brief highlights on this, but most of this is details that we just, again, can't justify class time for. So I'm actually going to kind of draw the line right there. I'm going to draw the line right there. We will come back and hit a few details about this. If you want to read through it, go ahead. Might be a good preparation, but we're just going to basically start at the bottom of this page. Y'all have a good rest of your Wednesday. See you later. Yes, see you later.